In the last lecture, we were talking about constraint satisfaction problems. We looked at how the CSP problem was different from some of the other problem solving issues that we looked at, for example, adversarial search and combinatorial optimization. And we saw how the age screen problem was a typical example of a constraint satisfaction problem. We looked at how the constraint satisfaction problem is a factored view of the environment, which was different from the earlier views of the environment, which were up till now atomic. Okay. And today, when we start talking about the next aspect of this course, which is knowledge-based agents, we will also see that they will also be looking at a slightly more complex view of the world. They will be looking at a structured view, okay, in some cases, and some cases, perhaps simply as in chapter 7, they'll simply be looking at a factored view, okay. And so we looked at the example of the map coloring problem, and we saw that there are various ways of solving this, and some of the issues that we tried to address were how do we actually improve the simple search which was being conducted using a breadth first search or a depth first search. And we also saw the examples of cryptarithmetic, which was also an example of a CSP. There are other examples of Sudoku and so on. And we looked at how to actually solve the map coloring problem using a backtracking mechanism, okay? And we asked ourselves the question, how do we actually improve the backtracking method, okay? Let me put this over here. And we saw that there was not only a backtracking method, but also a forward checking method, which we looked at last time. Okay. And now the question is, what are further improvements of either the backtracking method or the forward checking? Now, just to collect our memory, if you remember in forward checking, what exactly were we doing? Can somebody remind me as to what we were doing over here in forward checking, as opposed to backward checking? Backtracking, what are the basic differences? What were we doing in backtracking and what were we doing in forward checking? Right. So that was what, backtracking or forward checking, right? And what is backtracking doing? No, but it wasn't a breadth first search or depth first search simply. There was some difference between a normal DFS and backtracking. What is that? Yes. So we tried to reduce the tree search, and we would immediately check whether the compatibilities were being done at every stage. Okay, so that was a basic difference between backtracking and forward checking. And some of you suggested what could be further improvements. So let's take a look at this example. If you have this particular scenario and you have the option of either choosing B in the next stage, you've done A, you've colored it, let's say red. And the next question is, should we choose either B to be colored with, let's say, green, or should we choose F? So what was the logical answer to that? You choose F. Why is that? It has more constraints. Okay. So the simple answer was that we want to choose the variable with the fewest legal values. In other words, we want to look at the most constrained variable first. Okay. It sort of makes sense that if you've done A, the next thing actually, even before you do A, you would have started with F. But let's assume that you've done A, then naturally instead of doing B, you would have done F, because F can be seen to be a lot more constrained in terms of the options it has. Okay. What other improvements can you make? So here's another example. Let's say you've done both A and B. Okay. And now you have the choice of either doing C, you either color it red, or let's say you're not looking at F. All right. You're being silly. And you're looking at either C being colored red or C being colored blue. Now you've already given A the color red and B the color of green. Okay, so would you choose C to be red or would you choose C to be blue, a third color? G. Okay, so what are you suggesting? Yeah, so you can see that if you chose blue over here, then obviously you've got a problem over here, right? Because now you've run out of colors. You only had 3 colors. And essentially what you've done is you've reduced a subsequent step, okay? And some of those adjacencies will have a problem. So it makes sense to use C as the same color as A. And so the thought process is that the least constraining value, okay? So constraining means that it has the least constraints on a subsequent edge or subsequent color, okay? So it has the least constraining, all right? So it's a verb, okay? So you would choose C because it doesn't constrain F, perhaps D and E as well, but let's just look at F. It doesn't constrain F as much as choosing C to be blue is, because C would then, that would imply that F would actually have 0 values left, okay, because you've already chosen C. So you can see that these are 2 different criteria. One was most constrained variable, which means that it itself, you were choosing the variable which was most constrained, and the other was that it was least constraining on others in a subsequent step, okay? So these are 2 different criteria that you could use, and I'm not going to go into a lot more detail, but these are examples of ways in which you could actually improve the search, okay? Let's take a look at one more procedure that is used, and that allows further improvements, okay? So this is something called arc consistency, okay? Arc consistency means that let's say you have an arc x to y, which means that they're both adjacent, and so you look at both arcs x to y as well as y to x because they're both adjacent to each other, okay? So you would choose every value of x. For every value of x, there is some allowed value of y. So you want to make sure that if x on the arc x to y, for every value of x, there has to be some allowable value of y. Okay, so let's take a look at this. So here x has been selected to be blue. All right. Now y is this is an arc which is linking x and y. So does y have some allowable values if x is chosen to be blue? Right now, y has the colors, possible colors, red and blue. Okay. Now, if we choose x to be blue, does y have some allowable values left? So if x is chosen to be blue, can y be blue? No, because they're adjacent to each other. So you're going to subtract the blue color. Does y have any color left? Yes. Okay. So we're using the same paradigm that we were doing earlier. We have all the colors that are still available over there. So it has 2 available colors. Now, clearly, in this case, it is okay. The arc is consistent. Why? Because for every choice of color at x, y will have some allowable colors. So there's only one possible color at x, which is blue. If you choose that, then y will have red. You'll cross out blue, but you will still have red. Now, if you look at the same case in the other direction, in this direction, now for every color in x, does y have an allowable color? So if you choose red, if x is red, does y have an allowable color? Yes, it does have. So y could be blue. They won't be the same color. They're adjacent, but they're not the same color. But what about x? Right? So we're going back to the situation where x was still red and blue. Okay? So we're looking at that scenario. If you choose x to be x to be blue, then would y have any color left? Clearly not, right? Because these two can't be the same color. So in other words, this particular case is not consistent. Okay, so this arc is not consistent. You would have to reduce, you would have to remove in order to make this arc consistent, you would have to remove the blue color from X. Okay. So this is something called arc consistency. And if this is done, then it further improves the entire search. Okay. And you can read up a little bit more about it if you want in the book. I don't want to spend too much time here. We can also use the local search for solving this particular CSP. Okay. So we've spoken about, backtracking, forward checking, arc consistency and all of that. But you can also revert to something which we've already seen before, which is local search. Okay. Now, how would local search work? Basically, what you would do is you'd start off randomly. In the local search, what would happen is that you start off with some random scenario, and then you have some kind of a criteria. It could be some heuristic. For example, you could have minimum conflicts, right? Now, earlier we didn't have a mechanism to address this, but now we do. So we've got enough information about the variables. We know exactly where the queens are and so on. So we can actually figure out what the number of conflicts are. Okay. So once we figure this out, so let's say we want to reposition this queen, you look at how many conflicts does it have in each one of these steps. So right now it has how many conflicts? It has, I think, 3. It's got this one here. And so in this particular case, it only has one. Sorry. So in local search, you're trying to find out other solutions, right? We've said that you could actually do a complete tree search, okay? And we said that you could use backtracking, and you could use forward checking, and you could use arc consistency to be able to reduce the entire tree size, okay? But even all of those techniques in this particular case actually don't get as good as results as if you did a local search, okay? So if you do a local search, let's take a look at this. What it will try to do is it will look at the number of conflicts, for example, in this position. So if you go here, you've got this conflict and you've got this conflict, so there'll be 2 conflicts, okay? If you go here, you would only have 1 conflict like you have right now. In this position, you would have 3 conflicts and so on, okay? So what you could do is you could randomly choose any one of those conflicts where the number of conflicts are minimized, okay? So in this case, the queen jumps over here to this particular point, okay? G. यहाँ पर 3 पहले वाली में यहाँ पर 3 कैसे हो रहे हैं? Because there's going to be 1 conflict with this guy and 1 over here and 1 over here. Okay, so there are 3 queens, and so you pick one which is going to minimize the conflicts, but you pick it randomly. Okay, so you come over here. Now the next thing you do is you do an iterative solution. So you say, well, now if I get over here, what about other people? All right, so let's take a look at this queen. How many conflicts does it have right now, and can it move to another position which also minimizes its conflicts? Okay, so again, it chooses different things. If it comes over here, it will have conflict over here, here, and so on. But it finds out that it has a position where it will have no conflicts. Okay, so this particular solution becomes an optimal solution in this case. Okay, and all you had to do was try an iterative technique, okay, and use minimum conflicts as a optimization criteria. Okay, so basically, if you look at different examples, and this is an example from Russell and Norvig, it says that if you use the n queens and if you use backtracking, okay, and I think n in this case is not 8, it's a bit larger, I forget what it was. But and if you use forward checking, in both of these cases, even after 40 million steps, it wasn't able to find a solution. Okay, but using minimum conflicts, it was able to find a solution after 4,000 steps. A huge improvement. Okay, if you do the map coloring and you use not Australia but the USA, which has 48 contiguous states, then after 1 million steps, it wasn't able to find a solution using backtracking, but using forward checking, it was able to find a solution after 2,000 steps. Huge improvement. Okay, And with minimum conflicts, it was able to find a solution with only 64 steps, 64 iterations. All right. And then there's this other CSP problem, which is about, animals and cities and so on. But this is just to tell you that, again, there's a huge improvement when it comes to doing things using different algorithms. Okay. In all of these, is a solution guaranteed? Does it always find a solution? In a CSP problem, even if you're using minimum conflicts or forward checking or backtracking, as opposed to using a depth first search or breadth first search.
That would have been covered in the PFS or DFS.
Right. So actually, say all three of these techniques, you're not guaranteed to find its optimal solution. Okay, as opposed to the DFS or the depth first or breadth first, there you always find an optimal solution. Of course, it could take you, more time than you have available, but that is one of the advantages. So this now completes the first two major sections of the book, Sir Novik. Okay, and now we'll go on to the third main section, which is knowledge, reasoning, and planning. Okay, and as some of you might have thought about in the early sections where we talked about different types of agents, you said that, as I said, what would be your technique to be able to, get to the IBA, for example? And some of you mentioned that maybe if we had some kind of knowledge about, the existing cities, further details about the actual information about the system, about the environment, right? And we could actually improve our search. But so far we said, well, we'll talk about that later on. So now this is the time when we actually want to talk about where you actually have a knowledge base. Okay. So if you think about knowledge-based systems, you could use knowledge-based systems to solve complex problems. For example, you've heard of expert systems, which are often used, and they have a database, okay, and they're using that database, for example, to solve a problem. So, for example, if you have a medical system, right, so you could have a huge database of all kinds of problems, diagnoses, and diseases and their diagnosis and so on. And you could have facts and relationships amongst them, that if you have this particular condition, then this is probably the disease and so on. So that complex knowledge-based system could actually give you a lot fewer searches as compared to other searches that we've looked at right now. So far, we've looked at a fairly simplistic way of being able to search for problems, right? So when you have such a database, okay, then you also need to have a representation system. Okay, so actually, how do you represent the information in that database? Okay, you've taken, I think you haven't taken databases yet, but you have taken data structures, right? So you have an idea that how would you actually create your data structure? Okay, so the data structure sort of indicates that you need to have a mechanism to be able to, not at the physical layer, but a slightly higher level. How do you actually represent the data? So that's what we're going to talk about today. Okay, so you need a mechanism to describe the facts. Okay, you also need a mechanism to encode rules. Okay, so you might say that these are the different diseases that exist. These are the different symptoms that exist. But what is the rule between a symptom and a disease? All right. So if you have a skin infection, what kind of disease is that indicating, right? So you have to have some relationships as well. So you can think of facts perhaps as nodes, okay, and the relationships as maybe arcs. Okay. So if you have two objects, you might have relationship between some of them, but you may not have a relationship between all of them. Okay, so just think about this graphical description as well as you go forward. And also, finally, you need to be able to query the knowledge base. Okay, a knowledge base is useless if you can't actually ask information from it and get answers. Okay, so these are different things that we're going to talk about, both about the knowledge base, okay, which we're going to refer to it as KB, and about the representations of it and the different things that we need to be able to do with it. Next, what we need to also do is have a reasoning system to derive knowledge. Okay, so you may have a static knowledge base, but you may be able to derive further information, derive inferences, as we refer to them, from the existing database. Okay, and let's take a look at a few examples of this. So what are the different ways in which we use inferences or reasoning, as you might say? Okay, and actually, if you think about it, we're all using reasoning all the time. Now, one way could be intuitive, okay, and the other way could be logical. So intuitive may be very subjective. So for example, I remember one of my bosses here used to say that if I look at another person and the other person doesn't look into my eyes when he's talking to me, then I think that he is unreliable. Okay, and he had a lot of experience. He was actually one of the directors at IBA, and he met one of my colleagues who was very trustworthy to me, and immediately said, "This guy's not looking into my eyes, and so I think that he is not very trustworthy." I was kind of shocked. All right, so was that subjective or was that logical? That inference that he had, it was fairly subjective because it was drawn from his personal experiences. Okay, he might have had 100 people working for him in the past, but that doesn't mean that every single individual in the universe will have that feature. Okay, so it's sort of an intuitive reasoning. It's still reasoning, okay, but it's an intuitive reasoning. Okay, the other way is a logical reason. Okay, so for example, my wife as well, when she sees somebody new, she immediately has an intuition that that person is trustworthy or not. Okay, I'm a fairly logical person. I don't have that intuition. Maybe I'm missing something in my life, but I don't have that intuition. I can't really say, well, how can you say that this person does not seem reliable? Okay, I would go on logic, right? And I would say, well, this person, if he's unreliable, I need to have some facts. I can't just say that he looks or he acts or his body movements or his body language is in such a way. So if you remember, in a lot of movies, you say when there's a murder or something and the cops go to some lady and she starts talking about all of these things happen, and the cop says, "Just the facts, ma'am, just the facts," right? You must have seen this. So what is the cop really saying? He needs to have just the facts. He doesn't need to have her intuition as to what's going on, not what she thinks who could be the person who actually did the crime and so on. He needs to have the actual bare minimum facts. Okay, so that is what logical reasoning is about, is that we want to have the facts. Okay, and what do we mean by facts? We'll talk about those as we go forward. Okay, so for example, if I'm looking for somebody who's unreliable, I would say, well, let's take a look. In this particular scenario, let's say at 2 o'clock, we were in our room and everything was fine. We went away for 2 hours. We came back after 2 hours and some money was missing. Okay, so I would look at the logic. I would not say, does this person look suspicious? But I would say, well, who was inside? Who had access to that room? Okay, and if I say there's only one person who had access to that room, and I'm 100% sure that the money was there at 2 o'clock, and nobody else had access to that room between 2 and 4, and at 4 o'clock the money was missing, then I can do a logical inference that this particular person who had access was actually the culprit. Okay, not the person's looks and so on. Okay, so this is logical. And then there are different ways of doing inferences. Inference basically means you draw a conclusion. Okay, you could do a deductive deduction or induction. So deduction normally says that you go from general to a specific. Okay, so for example, you say that all mammals are animals. Okay, and then you say a cat is a mammal. All right, so can infer that a cat is an animal. Okay, fairly straightforward. And this is going from the general to the specific. Induction is a little bit more tricky. Okay, there you're trying to develop a theory. Okay, so you would say, well, the observation is all cats are animals and have 4 legs. Okay, you also see that dogs are animals and have 4 legs. So we can try to draw a theory, and you can say that all creatures which have 4 legs are perhaps animals. Okay, so that's an induction process. Okay, and that's developing a theory. So so far we're going to specifically look at deduction. Okay, in most of our inferences that we're going to go forward, but you may look at induction as well at some point, but initially we'll start looking at deduction inferences. Okay, Now, logic is extremely important. As I said, I've been giving you the example of a logic when I tried to draw an inference. Okay, so I said that the person I use what are the facts, and from those facts I can draw an inference. Okay, so there are different types of logic. So the first type of logic, which is the simple type, which will be discussed in chapter 7 of your book, is what is called a propositional logic, or what is also referred to as a Boolean logic. Okay, and this is differentiated from first order or predicate logic, which is discussed a bit later. Okay, so a proposition, basically, when you say, you're having a discussion, and we say, well, what is your proposition? Okay, that's, you might have heard that in arguments. So a proposition simply is a fact. What are you actually saying? Okay, now other people can discuss it, whether they agree with it or disagree. They think it's a true proposition or it's a false proposition. But a proposition basically is something which can be reduced to a Boolean value, which it is either will be true or it will be false. Okay, nothing more than that. Very simple. No, it's not intuition. So you can see that intuition is, intuition is subjective. If I say, so facts versus opinions, that's a good example. So G. So no, there won't be a probability associated with it right now. Okay, propositions right now will either be true or will be false. Given a particular scenario, it will either be true or false. It can't be both. If it can be both, then it is not a proposition. Okay, so something which says that this person looks suspicious is not a proposition. Okay, so so for example, you could say cats are animals, cats have 4 legs, and so on. Those are statements. Those are facts. Now, you could say cats have 3 legs. Okay, is that a proposition? It is a proposition because it is a statement. Now, is it true? Well, some cats might be having 3 legs, but generally speaking, most cats have 4 legs, right? So it's a false proposition. So propositions can have a true or false value. Okay. Now, similarly, you can have combinations. So combinations, you could say cats are animals and cats have 4 legs. That's still a proposition. Okay. Or you could have a combination with an or. But even if you combine it with, and you've studied Boolean logic, you could combine these propositions and still that at the end of it, it will either have a true or false value. Okay. And you look at some other examples as you go forward. Then we also have, we could also have relationships. Okay, not relationships, but we could also say that if something, then. Okay, so if a cat has 4 legs, then that implies that a cat is an animal. Okay, you could also have a relationship which goes both ways. Okay, so you could either use single arrow or you could use double arrow. Okay, for simplicity, I'm going to use single arrows. Okay, can't be bothered with 2 arrows. So you could have it both ways. You could say if and only if. Okay, so let's take a look at some more examples of those as you go forward. A predicate, on the other hand, will be more complex. Okay, it will have a relationship. Typically, it will have verbs, adjectives. Okay, some kind of relationship between 2 nouns. For example, somebody is a brother of somebody else, or somebody went home, or somebody hit somebody. Okay, so you can see that now verbs are coming in. You could say somebody is tall. Okay, so now it's an adjective which is describing somebody. It's not a simple propositional statement. Okay, so those will be referred to as first order or predicate logic. Okay, so now let's first of all, and then there are higher order logic which we'll not discuss right now, but those are nested predicates. Okay, so let's take a look at the first case. Now let's try to understand propositional logic. Okay, so some of you, I'm sure you've already, I think I've probably covered this in my introduction to computing course as well. So if you have 2 propositions, P and Q, okay, you could have not of P, which is very obvious. You know, if P is false, this becomes true, false, true, true, false, true, false. Okay. If you have two propositions, you could have a not of P, not of Q, or you could have an and of those two. Okay, so you could, and this operator here, this symbol represents an and this represents an or. Okay, the way I remember it that is that this looks like an A. Okay, this looks like an and. So so this is if you and the two, then clearly if both of these are false, this will be a false. If false true, this will be false. True false will be false, and true true will only be true. If you're doing the and operation, if you're doing the or operation, clearly if any one of them will be true, then all three of them will be true. That's kind of obvious. Okay, but here's an implication. Okay, what we're saying is that if P, then Q. So now it's not kind of obvious that in this case, if P is false and Q is false, is this going to be true or false? So how many people think it's going to be false? How many people think it's going to be true? Okay, so you're saying most people think that this will be true. Okay, can you explain that? Yeah. So exactly. Right. So one way to think about this is if you use sets. Okay, and if you use, for example, you've covered Venn diagrams, right, at some point in your life, right? G. Okay. So it's probably the same example. So if you're saying P implies Q, then is P a subset of Q, or Q is a subset of P, or they, are they disjoint, or are they overlapping? What does P implying Q indicate in terms of sets? So who's a subset of who? P is a subset of Q, right? So it will not be any one of these. It will be something like this, right? So this will be Q. So for every value of P, if P is true, then Q is also true. Okay. So so we're saying that if, for example, an example could be that P could be all computer science students of IBA, okay, and Q could be all students of IBA, right? So if you are a computer science student of IBA, then clearly you're also a student of IBA. That's a bigger set. Okay. So P implies Q, and if you say P implies Q and Q implies P, what does that mean? Where is Q now in this case? Sorry? It's going to be a subset. Is Q going to be in here? It'll be exactly equal, right? So P and Q will be exactly the same. So my drawing is not perfect, but it's supposed to be identical. Okay, because that's kind of obvious, right? So what we're saying over here is that if P is false, then Q is also false. So if P is false, in other words, over here, if P is false, then there are some solutions over here where Q is also false. Okay, not all of them, but for example, over here, this is a possible solution. Okay, so when P is false, and Q is also false, then that solution is a valid solution in your entire universe. Okay. Similarly, if you say that if P is false and Q is true, does that make sense? If P is false and Q is true, can you find a solution over here? It could be a BBA student, right? So it could be over here. So that would also be true. Okay. So if you look at this, these two will be true. Okay. True and true. What about over here? If they're both true, then clearly that's going to be true. But what about this? When P is true and Q is false? P is true. In other words, you're a computer science student at IBA, but you're not an IBA student. That's not possible, right? So clearly this is the one that's going to be false. Okay. So so it's a good way to think about it in terms of sets. So you can see that this is true, true, this is false, this is true. Okay. If P implies Q and Q implies P, then clearly these two are not possible. This is going to be the only case that's going to be, these two are going to be true. Okay. So this is some thoughts about propositional logic. Now, there are a lot of logical equivalences, and hopefully you've studied this at some point in your life. So you've studied in discrete math. So if you look at this, for example, if A implies B, then this B, I sometimes I write it as B bar implies A bar. I think you can think of this as well. Okay, if A and B bar, is that equivalent to A bar ORed with B bar? Okay, so you've gone through all of this. You can look at different examples of this. Another case, which is a little tricky, I don't know if you've come across this. Here we're saying that A implies B, and now we're replacing this implication with this statement. Can somebody explain what that means? So this is saying that these two are equivalent. Okay, this statement over here is equivalent to this statement. Even though here on the left-hand side, you make an implication that A implies B. Okay, and on the other side, on the right side, you don't have any implication. How can these two be equivalent? Truth table se nahi hal hoga. Okay, so you can do it. Let's do an intuitive way. Okay, so think about this, but I won't spend too much time on this. But basically what this is saying is that if A is implying B, so let's assume that A is a subset of B, okay? A bar ORed with B will be what? So I'll just show you the solution over here. A, not A, ORed with B will, so not A is all the yellow stuff, okay? And the red stuff is B, okay? You've taken the union of those two. Does that cover the entire universe? It covers the entire universe, right? But if suppose that A is not a subset of B, okay? Let's take this particular example, okay? Here A is not implying B, right? In the second example, because this is false. A is not a subset of B. Now, in this case, if you take not of A and you take a union with B, does it cover the entire universe? This yellow part will be left out. Okay, so the yellow part will be left out. So in other words, this will not always be true. Okay, so this sort of making the equivalence between these two, you can see that in one, the left-hand side sort of implies the right-hand side. Okay, anyway, so this was a little bit about the first part, which is types of logic. We spoke about propositional logic. Okay, and we saw how you can use different operators as well on propositional logic to have combinations of those. Now let's take a look at first order logic. And in order to do this, what I'm going to do is I'm going to introduce you to Prolog. Okay, so Prolog is one of the programming languages. You probably haven't come across this so far because it's a little different from normal languages. Okay, why is it different? Okay, it's not a procedural language. So if you think about all the languages which are procedural languages, in procedural languages, you tell a computer how to solve a problem. Okay, so any one of these languages are essentially telling how to solve a problem. Okay, in a declarative language, which is Prolog, okay, you're not really telling it how to solve the problem. You're specifying a goal. Okay, so far we've talked about searches. So you're specifying a goal, and Prolog figures out how to get to that goal. Okay, so Prolog is going to be deploying some of those search techniques that we've been talking about. Okay, G.
So nowadays we have much flexibility with the procedural programming. We can also.
You can do that. You're absolutely right. So actually, a lot of times people say Prolog is dead and you don't really need it. In fact, if I ask some people overseas, they don't use Prolog anymore. They actually use everything in Python. So you can do everything that you want in Python as well, or any procedural language as well. But Prolog sort of is simpler version of it, and it builds in a lot of the things, so it's a bit easier to introduce the concepts. Okay, rather than doing the same thing in Python, which I could have done, it would have made it a lot more complex. Okay, so let's use Prolog because it simplifies the understanding predicate logic. Okay, so we'll use Prolog over here. And the way Prolog is implemented is that it has both propositional logic as well as predicate logic. Okay, and we look at some of those examples in the next 10 minutes. Okay, so not only do you actually specify the facts, so far in propositions we've only specified facts, okay, which can either be true or false. But here you also have objects. So you've studied object-oriented language, so you know what objects are. Okay, and you also have relationships. Okay, so you can think of methods and so on in OOP where those relationships are also indicated. Okay, then you also have rules. So these rules govern objects and their relationships. Okay, and we'll take a look at some of these examples. Finally, you can also ask questions. Okay, now you must be thinking that, yes, I could do all of this in C++ or Java, right? Yes, you can. But what we'll use is Prolog to demonstrate the concept. So let's go forward. So in Prolog, there's a certain syntax. Okay, so every language has its own syntax. So here you could have any statement over here, and you must end it with a period or a full stop. Okay, which basically means that this is now a fact. So now if you do a query, this will, and you can, so these are all facts. You can say raining dot is a fact. All of these are facts. Okay, they don't mean anything right now. You can think of it. They might mean something, but they're all given as facts. Okay. Now you can do queries. So as I said, you can also do a query. So if you said sunny period, okay. Sorry, you chose a bad example. Sunny wasn't over here. So for example, if I said running, if I said raining, and I put a period over here, this would be a separate interface, and it would return true. Okay, why is that? Because raining has been defined. It's an object. If you said foggy, it would return an error. Depending on which compiler and so on you're using, interface, it would either return a false or it would return an error. Okay, and so on. So, so you can now next also do relationships. So this is where predicates come in. So now we're talking about first order logic. So I could also say that X1 is a male. So for example, if I wanted to have a tree, which is a family tree, and we're trying to say that X1 is the parent, and X21 and Y21 are its two children. X21 is male, and Y21 is a female. Okay. So what you could do, if you simply wanted to state a fact, then you could say X21 period, which would indicate now that X21 is a fact. If you queried it X21 period, it would return true. Okay. If you said X9 period, it would indicate an error. Okay. So for example, you could, right. So similarly, now I'm indicating relationships, and I'm also indicating that these are facts. So I could say that that X1 is a male. Okay, and male here is now is a predicate. Why? Because it's indicating a property of X1. Okay. Similarly, you could say that Y21 is female. So Y21 is a female. So this is indicating a property of these objects. Okay. So these will again simply be facts. And if you did a query, for example, if you said male X1 period, it would return a true. If you did female X1, it would return a false. Okay, even though we haven't defined anywhere female X1, it would still return a false. If you said male X9, it would return a false. Okay, because this predicate has been defined. But if I haven't defined this gender, which is I haven't defined this predicate, and I said gender X1, it would actually return an error. Why? Because the predicate has not been defined. Okay, this is how Prolog works, and it's and there are different versions of this as well. Okay. Now you can also do variables. Okay, so for example, you could say if you so far if you notice that everything that I had used, all of these were lowercase. Okay, x1, y1 were all lowercase. However, if you want to in Prolog, if you want to use a variable, you simply make the first letter uppercase. Okay, so if you said male x, okay, then it's going to actually do a query. Okay, and x is going to be uppercase, so x is uppercase, so it will interpret it as a variable. Okay, and it will try to search for a solution. Okay, so it will give you x is equal to x1 and x is equal to 21 in this, well, not in this case, but if you had a bigger case. Okay, so I've got, for example, if I look at this case, so here I'm defining x21 and I'm defining a number of offspring of x21, right? So for example, if I said male and I said capital X, so if I said male over here and I said capital X, all right, what should this respond with? And I've defined all of them. Right, so it will respond with all of the x's, right? x31 will respond with x31, x1, x31, x21, x32, x41, right? And similarly, if I said, and I could have also written this as male and who, okay? So because who is starts with an uppercase, it will treat it as a variable and it will respond with all of the possible males. Okay, so this is how Prolog works. You could write anything. So you could write, male what. Okay, it will still work. May not make sense in English, but it will still work. So say that again. What are you writing? Yeah. यहीं पे हम क्या लिखें? W. So I write male and WHO. Yeah, the same output. Yeah. So it will treat both of these as unknown variables. It'll give the same response. Okay. And I will ask you to download Prolog. You don't even have to download in some cases and play around with it. This will be a useful experience. So you can also show relationships. For example, you could say x1 is the parent of x21. Okay, so x1 is a parent of x21. This is how you would write it. Okay. Now all of these, notice, are lowercase. So there are no variables being used here so far. Okay, so you could say x1 parent x1 y21, which indicates that x1 is also parent of 21. Okay, now if you did a query, for example, you said parent x41 x21, then it returns a true. Okay, why is that? Because it will treat these as constants. Okay, and it will try to match if this in fact is one of the facts. Okay, but if you said parent WHO x21 is going to return x1. Okay, is that making sense? Why? Because who was a variable. Okay, so it tried to find all the matches where x21 was a child of this. Okay, so it's basically saying who is the parent of x21. Okay, so you can see how parent who x21 answers the question who is the parent of x21. G. Sorry. Okay, so I got this wrong. Yeah. So this is, so I've got some of my logic over here wrong. I'm glad you pointed it out. So it should have been x1 over here. Good. Somebody's paying attention. So that's a good point. So you have different interfaces. So the knowledge base is normally in a separate file. Okay. So let me just show you how it would work. So let's say that this is the interface for SW log. All right. So let me just restart it. So if I want to, so let's say I go here and I started Prolog, it would come up over here. And now I'm going to consult the knowledge base. Okay. Now I've already got a knowledge base over here, which I've written down over here. Now it says that it has 20 clauses. So this is the interface for SWI Prolog, which is the most popular version of it. And when I did a file consult and I opened up this particular file, okay, which had to be written with a .pl at the end, this is the knowledge base. Okay. Now what does it look like if I show you the knowledge base that I have? So it has comments and it has all of these declared. Okay. So some of these are the facts. You can see male x1, male x21, and so on. Then you have some of these relations. Okay. So I'm saying that x1 is the parent of x21 over here. Okay. Then I can also draw functions, but I'll look at that in a minute. So this is, so your question as to how do I know that this is a query or is this a statement, is because they're in different locations. Okay. There's also another version of this which can be seen online. So this is Swish. I hope you can see it. So Swish is has the two in the same. It's in sort of an IDE. Okay, so you can write your database, the knowledge base on the left-hand side, and you can do a query over here. So if you want to do a query, for example, you said x31, and you did a query over here, it returns true. Okay, but if I did x39 dot, and I did a query, it says that x39 doesn't exist. Okay, so this is how you're differentiating between a query and a statement. Okay, so so now you can also have functions. So here's a function, and what you're trying to do is define a function which accepts two variables f and c. All right, f and c, and it says that f is a father of a child if, well, this was he, is a parent of X and is male. Okay, so how would you do that? You would say, you would use this particular syntax to indicate that you're defining a function. Okay, and it would return a true if both of these are true. Okay, and they have to be separated by a comma. Comma simply means that this is an AND function. Okay, so C and F, so F is a parent of C, as well as this returns a true. In other words, for the same value of F, it has to be, this particular portion has to be true as well. So if both of these are true, then this is going to say that F is a father of C. Okay, so for example, if I say father x121, then it's going to return true in this case. And if I said father who y21, then in this case, it would return x1. Okay, so that's a function. Now let's try to see, well, time is over, but think about how would you write a sibling function. So let's do a quick think on this, just take another couple of minutes. How? So the same father. Okay, so that's good. So you would use a father function to be able to, so you could say that sibling S1 and S2 are siblings if P is a parent of S1 and the same P is a parent of S2 and S1 is not equal to S2, because you don't want to have the same person. Okay, so X21 is not a sibling of X21, but X21 is a sibling of X20 of Y21. Okay, how about this, first cousins? So father siblings, right? So you would basically say if the two fathers or the two parents are siblings, then they're first cousins. Okay, and they're not the same. So So you could think about that, it could become more complex. Or you could say, you could define a grandfather. Okay. And grandfather, similarly, you could define a grandfather, which could say that if the two grandfathers are the same, then you are first cousins.